Hi class, and welcome back to Calculus. So today we're going to talk about Green's theorem some more as a planimeter, and we will explain that. But first, today's recommendation is the album Morbid Stuff by the band Pup, spelled all in capital letters. This is a punk album. It is shouty, it is loud, and sometimes it just really feels cathartic to listen to that sort of stuff. I want to especially highlight this song "See You at Your Funeral," where the protagonist of the song is singing about how he does not want to see his ex ever again, and in particular, in the second verse, there's this just awesome lyric where he sings, "I wonder what you thought seeing me in the produce section." Buying organic food, making healthy selections, and it's raucous. It's kind of funny in a dark way. The whole album, and it's definitely got an explicit warning, but it's just fantastic. So, highly recommended. So today we're talking about Green's theorem in the context of a planimeter, and the first question is, what's a planimeter? So I'm gonna give a link to some videos on YouTube. This is what I normally do in this class, is we would pull up YouTube and we'd actually go watch a video. So I'll send you to another video. So see video link below. But essentially a planimeter is a tool, an actual physical tool that engineers can use, tool for engineers, and I think architects actually use them all the time, where it's this tool that you drop a little head at some point on a page and you trace it around, and maybe you're doing some amazing outdoor pool design and you want to know, like, what's the area of this pool that I just drew, and because you want to know what's the square footage, because you need to calculate how many tiles you're going to buy to fill it, and whatever. And so you just have your perfect one-to-one scale drawing, and you take this tool and you draw around this loop around the region whose area you're trying to compute, and the tool tells you the area. It computes the area. So if this region is R, it'll compute the area of R, and it does it only using this path going around R. And this is Green's theorem, believe it or not. The entire thing runs on Green's theorem by doing some computational integrals, which you can design. So let's look at it from a mathematician's point of view. What does Green's theorem tell me about area? Well, Green's theorem said that if what I want, it tells me I've got this path C, and C is the boundary of R, my region R. My stylus is dying, but my other one is in my office, which is not accessible anymore. So boundary of C of some vector field F dot dp. And this is a closed curve. By Green's theorem, this is the same as the double integral over the region R of F as curl, of the scalar curl of F. So nabla cross F dA. And so the key thing, the way you can make this relate back to area, is if nabla cross F, if the scalar curl is 1, then this is just the double integral over R of 1 dA, which is the area of the region R. So if you can come up with a vector field F that for whom these integrals on the left, as long as you can make this easier than computing the area, then what you can do is compute the area by computing this flow over this path, this boundary of C. And believe it or not, these Planimeter tools that I will send a link to, they actually do this on the fly. You just draw a little loop and they will compute the area inside of it. Also, if you draw the loop backwards, they compute negative the area because they only work either clockwise or counterclockwise, whichever way they are set up to be oriented. And for us, for mathematicians, Green's theorem is always oriented counterclockwise. So the positive area for R is going to agree with the counterclockwise boundary orientation for C. So this sounds like a great idea, but it only works if we have some vector fields F whose curl is 1. And it turns out there's a lot of those. And there's a couple ones we've already seen that are really useful and very simple. So let's look at some examples of vector fields with scalar curl plus 1. And here are my 3 examples. You can either take f to be 0, x, because then the scalar curl is 1 minus 0, or minus y, 0, getting ahead of myself. And then the scalar curl is 0 minus 1, which is plus 1 as well. Or you can take, well, minus y, x doesn't work, but if you divide both of them by 2, you get the right answer. So we saw last time that minus yx has scalar curl 2, and so 1/2 of it will have scalar curl 1, because scalar curl is defined in terms of cross products, and cross products and scalar multiplication commute with each other. So I can pull out that 1/2 and get 1, but you could also take these derivatives independently to get 1/2 from the x term minus 1/2 from the y term, and that's in fact plus 1. So we're good. So what you can do is pick any one of these that works for you, that's easier to compute with, and you can, instead of computing the area, which might be complicated, compute this scalar, pass from the scalar curl side of the picture back to the vector field flow picture and ask what is the flow of this vector field along C. So we're going to replace the area of R with an integral over C of f dot dp for any of these vector fields with curl plus 1. So what's our most basic example? We take a rectangle, R, and we try to compute the area of the rectangle using the Planimeter method. So let's compute this. Using Green's theorem. So let's treat this as a proof of concept. We know the area of this rectangle is A times B, right? And so my picture for this should be something like one of my corners of this is at 0, 0. A x goes up to a. Here's my x-axis. And in the y direction, we go up to b. So here is my rectangle R. Let's give it some shades. Cool. So in order to use Green's theorem, what I should do is orient my boundary. So going counterclockwise, I'm going to treat the origin as my starting and stopping point. And moving counterclockwise around, I kind of have these four edges. Wherever you're going to have a corner, you need to change parameterizing functions, because it's easy to parameterize one of these sides, but then it's kind of hard to parameterize each of the other ones. So you should think about viewing the boundary of R as being made up of three subcurves, C1, C2, C3, and C4. And each one of those, if we parameterize this, let's parameterize that using P1, this one using P2, we'll use P3 for this one, and P4 for this one. Then P1 is for this side, P2 is for this side, P3 is for this side, and P4 is for this side. And so we're going to traverse each of these edges using different parameterizations. So the way I would think about this function is, so assume f has curl f equal to 1 to start, and we'll pick f later. And we can pick f to be any of the functions we outlined on the previous page. So the way I see this, the area of R, which I know is a times b, right? I know I'm going to get that as my answer, but let's make sure we can get there with integrals. That would be the double integral of 1 dA of R, which is this secret double integral of my scalar curl. And then using Green's theorem, let's just write it up here. Green's theorem, that's equal to the integral over the boundary of R, going counterclockwise, of f dot dp. And now I'm going to break that boundary integral up into four integrals that I'm doing, one for each face, and I'll write them out separately. So what that is the integral over C1 of f dot dp1 plus the integral over C2 of f dot dp2 plus the integral over C3 plus the integral over C4 of f dot dp4. Okay, and now for each one of these, I can choose a way to parameterize each of these functions. And the way I see it is P1, P2, P3, and P4, each of them has a constant axis. So I'm going to use that, like each one of them is either at 0 or at B or at A or at 0, in one of the components. So I'm going to use that to set up what P1, P2, P3, and P4 are. So you can pick different parameterizations, but my P1 will be P1 of t is just, well, the y component is always 0, and the x component goes between 0 and a, so I'm just going to make it t, and I'll make the bounds for t be 0 to a. That's very simple for me to write down. P2 of t, it needs to start, so here the x component's always a, but my y components change, and they go from 0 up to b. For P3, I'm doing my y component stays at b, but my x component starts at a and ends up at 0. So I can make that to be a minus t, where t goes from 0 up to a. And so doing this a minus t, it's switching my t's around so that when I'm at time 0, I start at the point a comma b, and I end at the point a minus a, which is 0 comma b. So it kind of orients things correctly. And I'm going to do the same sort of choice for P4. I'll just make it here the x component's always 0, and my y components are starting at b and going down to 0, so they'll be b minus t for the same reason. And that gives me all the data I need to unpack each of these separate integrals. And my only remaining choice is, what do I want f to be? And so I could pick either 0 comma x, or minus y comma 0, or minus y over 2 comma x over 2, and I have a choice. And for the sake of simplicity, I'm going to pick this first one. That's going to be my pick. Let's just circle it. Yeah. You can pick any one of these. They will all, I guarantee, get you the right answer. When to pick them depends on your function. For us, the parameterizations are all very simple. They're all lines. So I'm not really worried about integrating either one of these. The last one, though, looks the most complicated. And so you're going to want to reserve that one for when there's symmetry in the picture, by which I mean maybe circles or ellipses or something like that, where you might be getting sines and cosines and their derivatives and they're going to cancel each other. You just want to keep it in the back of your mind that you have this third option, because sometimes the 0x or the minus y0 ones, neither one is easy, but when you're doing both, kind of things can cancel with each other, and that's why the third one's nice. So let's unwrap each of these integrals. Okay. So I'm going to underline what I'm rewriting, that first one, right? So just that first integral becomes the integral of f dot dp. Okay, well, f is 0 comma x. So my integral for C1 should start with 0 comma x, evaluated at, so this is going to be f of P1 of t dot P1 prime of t dt. T goes from 0 to a. Okay, and plus, I'm going to figure out all these other ones later, okay? So for f of P1 of t, I take f and I plug in my x value and my y value from P1 of t into f. So f of P1 of t, let's write that in black. F is 0 comma x, so f is 0 comma whatever P1 of x is, which is t, dot P1 prime. P1 prime is just 1 comma 0, dt. And the really nice thing about that is that's just 0. So in fact, this integral is 0. There's just no contribution from that side of the rectangle. So the second integral, so let's now do this one in double underlines. So here was the first, here's going to be the second. we're going to do the same sort of story, and let's fill in what it is above. So plus integral, for this one, t starts at 0 and goes up to b. That just is me looking at my coordinates that I picked here. F of p, f is always 0, comma x, and then I look over at p, and x, the x coordinate is just a. So that's kind of interesting. It's nice and constant. P2 prime is, a is a constant, so the derivative of that is 0. And t, derivative of that is 1. So when I take the dot product of this, I get a, which is not 0. So I'm actually going to get something from this integral, dt. So that's the integral of a dt, t from 0 to b. Okay, and now I realize I've overwritten my integral. Got plenty more space. So for the third one, and let's switch over to green for this, I guess. My integral should be going from t equals 0 to a. F is 0, comma, whatever the x component of P3 is. The x component of P3 is a minus t. P3's derivative, only that minus t matters. So I'm going to get a minus 1, comma 0. And oh, look, that's another dot product which equals 0, dt. So I'm going to get nothing from that integral. And for the last integral, I have run out of space on that line above, so I'm going to write it below here. Let's tweak myself a little bit. Plus 0 plus integral. T started at 0 and went to a. I've got f, so that's 0, comma x. I go over here to P4. My x component is 0. Dot P4 prime, although I'm already dotting with the 0 vector, so it's going to be 0. 0, comma minus 1 dt. And you can see that this all is going to 0. So let's so here's the third one, here's the fourth one, first, second, yeah, looks good. So our final answer for this is we had 3 integrals where the flow was actually 0, and then the fourth one where the flow was interesting. And so our integral there is I'm integrating a dt. That integrates to give me a times t, where t is evaluating from 0 to b, which means I just get a times b, which I already knew was the area of a rectangle, but it is nice to be reassured that it is the area of a rectangle. I know this is a long example to get there, but and I want to point out something about flow for each of these choices of integrals. We could actually compute them from the picture, except for that middle, the one that actually evaluated something interesting. So if you look back at this picture, and you imagine drawing the vector field 0, comma x. So I'm going to draw the vector field. I'm sort of out of space, but 0, comma x, this is my y-axis, and this is my x-axis. It is never pointing up in the y direction. It's only ever pointing, it's only pointing in the y direction. It's never pointing in the x direction. And as you move farther out on the x-axis, it is pointing higher and like more and more steeply. So it's 0 here, and then it's up, then it's more up, and then it's more up, and it's more up. And those are kind of the same arrows as you spread out, right? And as you go to the left, it has arrows going down, and then longer arrows, and then longer arrows, etc. Hopefully this makes sense, what I'm drawing. So we actually saw this example in the last lecture as well. So if you look at this rectangle. On P1, my vector field the whole time is orthogonal to P1, so there should be no flow. On P2, the vector field entirely lines up with it, so there will be flow. On P3, again, it is orthogonal, so there's no flow. And then on P4, it's 0. The vector field is 0 because I'm on that y-axis where x equals 0, and so the vector field is just 0, 0. So you're dotting with the 0 vector. So just by looking at this picture, I already know that this integral over the boundary is 0 on the bottom face, the top face, and the left face, and the only place where it's non-zero is on the right face, and that agrees with our description below. You can do a similar analysis for the second option. I'm going to stop drawing, but just circle things. So minus y comma 0, that's a vector field that's always pointing to the left, and it's 0 on the x-axis. So it's going to be 0 on this lowest face because y equals 0 there. It's going to be 0 on these vertical faces because the vector field is perpendicular to them. It's pointing to the left. And then up here, it's pointing parallel to the surface and or to the side. So you're going to end up getting a non-zero integral. Hopefully that gives some intuition. Let's move on to harder examples. So let's compute the area of an ellipse using Green's theorem, not using polar coordinates or other fancy integration techniques. We'll just use Green's theorem. So let's draw a picture of our ellipse. Ellipses look something like that. So on the x-axis, I've got this intercept out here at A, and the y-axis, I've got one at B, and minus B. And so I'm going to let C be the curve going around this ellipse, the boundary of the ellipse. All right. So the ellipse, let's call E, and we'll let C be its boundary. So what we want is area of E, which we can get as the double integral of the scalar curl of one of these, one of our nice options, over E dA. And by Green's theorem, we can get that as the integral around C of f dot dp. Now, it's kind of easy to parameterize ellipses because they look just like circles, except they have different radiuses in the x and y axes. So my parameterization, p of t, is going to be a cosine t, b sine t. So this is a parameterization which starts, this is t equals 0 here, and then goes counterclockwise around. And this is like, you know, t equals pi over 2, etc. And so for this parameterization, t is between 0 and 2 pi. So there's a choice of what function or what vector field to use, and we're going to use f equals minus y over 2 x over 2. And we're using this because I know secretly it's the right choice. But again, the hint here should be you're looking for something where there's some sort of symmetry between what x and y are doing in this picture. And so like in a circle, it's kind of like, I mean, it's round. They're both involved in the parameters, and you've got these sines and cosines. And the only way you're going to get sines and cosines to cancel is if they can kind of talk to each other. So let's just run with this and see what happens. So I'm now computing integral over c of minus y over 2 x over 2 dot dp. Now, reminder, this is always, I take x and y from my p parameters, and I plug them in. So I set my t equals 0 to 2 pi. I plug p into my vector field, so the y component is b sine t, which becomes minus b over 2 sine t in my vector field. Right? And let's just highlight that in red. Here's my y. Here's my y. Right? And my x component over there is a cos t, so that's a over 2 cosine of t, close brackets. So there's x. It's surprisingly easy to mess up x in these types of problems. And then I need p prime. P prime is cosine's derivative is minus a sine of t. And sine's derivative is b, so b times sine t gives b cosine of t dt. And so remember, in case this is still feeling unfamiliar, this is your p prime of t, vector, times dt. You still have this dot product, so dot with f, but you've plugged p in to f. So you've plugged your x and y values in. And this is what you do to pass to the parameter t for the integral. So now let's expand this integral. So if I do the dot product, I get negative sine squared a times b over 2. So t equals 0 to 2 pi ab over 2 sine squared t plus ab over 2 cosine squared of t, and then times dt. And you can already see that you can pull out the ab over 2 in both of these, and you get ab over 2 times the integral of sine squared plus cosine squared, which is 1. Sine squared t plus cosine squared t, which is 1 dt. And since I'm integrating 1 dt, I just get 2 pi. So my final answer is ab over 2 times 2 pi, which is ab pi. That's now maybe the third time we've done the area of an ellipse. But it's the first time we've done it by passing to a one-dimensional integral rather than computing an area integral. So ultimately, we only did one integral in terms of t here in order to compute the area of this ellipse. We did a one-dimensional integral. So here's a question from, you could say, the real world, but an application of these planimeter approaches. Let's say you had this cross-sectional stump of a tree, and you wanted to know what the surface area of this was for some reason, right? Well, and let's say you also left your perfect planimeter at home, or all you really have is this picture, and or you haven't built a planimeter. How would you approximately figure out what the cross-sectional area of this is? Well, if you had a planimeter, what you could do is trace the boundary. So you kind of go around, and then something like this. And the planimeter would tell you how much area was contained inside. But if you don't have a planimeter, just drawing that curve didn't tell me anything, right? So what I could do is break the curve up into an approximation. So maybe just I pick a bunch of points along the edge, and I pick enough points that I feel I can approximate this curve not as a bendy curve, but as a curve made up of straight lines. So as a what is known as a piecewise linear curve. People also sometimes call these polygonal paths because it is made up of little polygons. So let's say you pick just a whole bunch of these points. I'm going to start picking them farther apart. And you approximate your blue path by these green dots instead. And yeah, you'd be missing little bits of area here and there, but you know, you're getting most of it, and maybe you're overestimating in a couple places, but you're basically getting a good approximation for the surface. And so once you've divided up your region into just a sequence of lines, now the question is, how do we find the area inside of that sequence of lines? So the new question is, what is the area encompassed by the polygonal path? It's also called piecewise linear. Notice that it is determined by a finite set of points. So what you could do is you can go up to this picture and maybe start naming the points. So you've got, this was where I started, so let's call that A0, and A0, well, it's really got an x0 and a y0 value. And then this guy here is x1 comma y1. And you keep going, and you know, this guy over here, he is xi comma yi. And you go around this last one here, this is xn comma yn. And then you have n different points. So in my description below, this path is determined by the points x0, y0, x1, y1, through xn, yn. And then if you were counting the edges, this last edge, which I'm going to highlight, kind of looks the same. Let's highlight it in yellow. Still kind of looks the same. Let's just draw it in yellow. That path right there. This goes from xn, yn to x0, y0. And so you only need these n points to determine the n line segments, because the very last line segment connects this last point to the first point. And so you could almost think that there's, you know, one more point, which if you want to think of the first, it's maybe wrong to call this the last, this is the second to last. The last point would be the point x0, y0, and then you kind of finish off your path. So you could maybe tell me this path at time 1, or time 0, I'm over here at this first point, and then maybe this is time 1, I'm at this point, and then I'm at time n here, time equal n here, and this is time equal n plus 1, and so in n plus 1 seconds I traverse this green path going around it. Yeah. So on the next slide, let's pare this example down and figure out how to compute it using Green's theorem. So let's try to find the area of this shape. Now I've put it on coordinate axes, so these points have easy x and y values, and that should help us actually compute the area using Green's theorem. So what we know is, so if f has curl plus 1, then the area is going to equal the integral of r of dA, which is the integral, the closed path integral over the boundary of r, oriented counterclockwise, of, which we'll call c, of f dot dp, of the flow. And when you split the boundary of r up into all these pieces, it's essentially a bunch of sub-pieces, which are each oriented counterclockwise, each of which is a line. So this big integral over c becomes an integral over, what you might call c1 of f dot dp, plus an integral of c2 of the f dot dp, plus, and so on and so forth. And in this picture, 1, 2, 3, 4, 5, 6, I have 6 of these. So there'll be an integral over c6 of f dot dp. I didn't number them, so all of this is the integral over c. I didn't number them in the picture, so you basically get to choose which is your starting point and which is your stopping point. So I think I numbered them differently in the back, but now I'm going to try to be consistent with the textbook. So let's just pick a point. So let's pick this point. This is going to be our start and stop, and we'll call this x1, y1, which means x1, y1 is 3, 1. That means this guy here is x2, y2, and so on and so forth, up to this guy here, which is xn, yn, and for us, that is x6, y6, and it happens to be the point 1, minus 1. So n is 6 for us. And so this first bit here is going to be c1, this bit here is going to be c2, etc., going around. So what we'll do is just focus on one of these little lines and try to compute f.dp over it. And the vector field we're going to work with is f equal to 0, x. Just seems kind of simple. So now what we'll focus in on is, imagine we're just doing the contribution for one of these guys. And so I'm going to do this for ci, and I is going to vary from being 1, 2, 3, etc., all the way up. And so when you're at one of these intervals, I want to figure out what this integral gives us. So what does that look like? Let's get a picture of ci. Let's say that's whatever orientation counterclockwise is. This is xi, yi. Here's ci, and here's xi plus 1, yi plus 1. And it turns out there's a really nice parameterization for this, where I can make this be times 0 and this time 1, and it goes at an even speed, constant speed in between the two. And the way to get that function is you just write p of t for this parameterization. Its x coordinate, I'm going to write it as a column vector because they're just going to be a little big, is going to be t times xi plus 1 plus 1 minus t times xi. And its y-coordinate looks really similar. It's t yi plus 1 plus 1 minus t yi. So you should look at this and realize that these are linear functions in t, so they have to define lines. That's why it's a line. But it's at time 0, if you plug in 0, the I plus 1 coordinates disappear. These ones over here. So you're left, and over here you get 1 times xi and 1 times yi, which is why you're at this point at time 0, and at time 1 you're up at this point, because you have just 1 times this, and 0 times these guys. So that works. And then our integral over ci of f dot dp becomes, when we pass to parameters, our time goes from 0 to 1. F is this vector field 0, comma x. My x coordinate is t xi plus 1 plus 1 minus t xi dot dp, so that's p prime dt. And p prime looks like xi plus 1 minus xi, comma yi plus 1 minus yi dt. And so if you're trying to keep up with this, this is p prime of t dt. And this one over here, this is f of p of t. Okay? So, turns out this integral is not that bad to compute, because my first coordinate of 0 for this vector field, which makes a lot of things nicer. So you're going to end up with the integral from t equals 0 to 1, when you expand the dot product of yi, and then we have to do some foiling, you get this. The yi plus 1 minus yi is a constant with respect to t. And then you also have t xi plus 1 plus xi, that's a constant, minus t xi. Those are being multiplied together, dt. And now this is a straightforward integral to take. You're going to get yi plus 1 minus yi times t xi plus 1 over 2 t squared plus xi times t minus t squared over 2 xi as t goes from 0 to 1. And so at 0, you're going to get a whole bunch of zeros, but at 1, you get this nice expression. Yi plus 1 minus yi times xi minus xi, so those cancel, xi plus 1 times a half. So the kind of cool thing about this is let's look at how this adds up. You know, this was our contribution just from CI to f dot dp, and we can pay this forward a little bit. If you'll see what happens on the next page. Okay, so on the last page we got this cool conclusion. So let's actually start expanding what this gives us for the answer. So you'll notice there's that 1/2. Just to make things easier on myself, what I'm going to do is multiply both sides of this by 2. And so I basically solve for twice what I wanted on all these parts. So I'm going to get 2 times the area that I want. that will just make my life easier, getting rid of the 1/2. So if I do that, these cancel in my expression. And then my ith edge is just contributing this product of xi plus 1 with yi plus 1 minus yi. So let's write this down. So the thing we want, the integral over c of f dot dp times 2, is going to be from c1, I plug in I equals 1 here, so I get x1, x2 y2 minus x2 y1. So that is my expression for C1. All right. From C2, what I'm getting is x3 y3 minus x3 y2. And then from C3, I get x4 y4 minus x4 y3. From C4, I'm getting x5 y5 minus x5 y4. From the next guy, I get x6 y6 minus x6 y5. And then we're actually back at C6 here. And C6 is a little unusual. I'm going to highlight it in green here, because C6 goes from the starting from xn yn, or x6 y6, to x1 y1. So actually, this last one, I plus 1, when I plug in 6, I don't want it to be 7, I want it to be 1 again. So I'm counting mod 6, or modular arithmetic. This is like counting on a clock. So this goes back to the very beginning. This goes to x1 y1 minus x1 y6. And so you can think of that as like 7 minus 6, because we looped around for those ones. And this gives you the area. But you might notice that there's kind of a, there's some repeating patterns here. And so there's this algorithm called the shoelace algorithm to help you compute these faster, to just do kind of all of the positive multiplications and then all the negative multiplications. Now, the standard way for using the shoelace algorithm, it's slightly more annoying to extract than this, because it uses a different choice for f. It uses f equals 1/2 minus y comma x. So it looks slightly different, but this should convince you that there is an algorithm like this, and you can use this to compute the area above or below. So let's summarize this. The way the shoelace algorithm works is and you get this from using f equals minus y over 2 minus x over 2. So the formula looks a little bit different, but it always gives you the same thing by Green's theorem, is you just make a list of all of your coordinates, x1, y1, x2, y2, for each of these segments, right? x3, y3, dot, 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 xn, yn, and then you also include that last loop around, because you need it for this C6 term is going to involve these two guys. So x1, y1. And what you do is you first multiply these guys diagonally down. So that becomes x1, y2 plus x2, y3 plus x3, y4 plus xn minus 1 yn plus xn y1 when you do the loop. And then you also need all of these negative terms. So these are like our positive terms up above, which for us have this different formula. The shoelace algorithm is nice because they're symmetric. So you do that, and then you subtract all the blue ones. And the blue ones go this way, which makes this look like shoelaces, like crisscross tied converses sort of thing. So that formula looks like y1 x2, so you can kind of just think about flipping the coordinates above, y2 x3, y3 x4, yn minus 1 xn, yn x1. And when you add this and subtract this, you're going to end up with twice your area. And so if you add this up, you get twice the area. Which makes your life somewhat easy. So on the next page, let's just use the shoelace algorithm to compute the actual area of this parallelogram we've been looking at. So let's compute the area using shoelace algorithm. So first I go down and it's positive. And these agree with the same negative positive directions as the determinant, which makes it easy to remember. So 3 times 1, I get 3 plus 0 plus 1 plus 6 minus 1 plus 1. So all of that adds up to 6, 7, 8, 9, 10. And my blue ones, which are negative, or will eventually be subtracted, look like that. They are 1 times 0, so that's a 0, minus 1, minus 6, minus 1, minus 3, minus 3. That gives me 6 plus 6 is 12, plus 2 is 14, so minus 14. Taking red minus blue, so my total area, or twice my area, is 10 minus 14, which is 24. So my area is 12. And you can confirm that if you break this up into triangles and squares and draw a little grid. You can absolutely double check that this area is 12. Have fun. So building off of that last one, let's use the fact that we know the area of R is 12 to compute this pretty weird looking integral around the closed curve C. So first, let us convert it into a vector field line integral. So to undot product, this looks like 2y plus sine x squared, comma, cosine y squared minus 3x dot dx dy. And this, I'm going to let this be f, and this is my dp. Then I will compute the scalar curl of f. It's two-dimensional, so this is kind of easy. It's minus 3 minus 2. And I'm getting that just from, here's the only y is here, here's the only x there. So even though the sine of x squared and cosine of y squared make the original integral look very hard, they don't show up in the scalar curl. So doing this integral as an area integral, as a two-dimensional integral, using Green's theorem is much easier. So this is minus 5. And by Green's theorem, the original integral that we wanted is equal to the double integral over r of the scalar curl dA, which is minus 5 times the double integral of r dA, which is just the area of r. So minus 5 times the area of r, which is 12. So negative 60 is my flow. And that's where we stop for today. See ya on Friday.